Hello and welcome back to the channel, guys. I hope you guys are doing absolutely fine and have been enjoying the data science series so far. Now today we'll be starting module 3, that is modeling. We have already covered 2 modules, and if you haven't checked those already, I recommend you to go and complete them first. Also, I have put up a PDF in the description that explains the entire structure of this course, so you can refer to it. Now let's quickly refresh what we have covered so far in the 2 modules. So in the first module, which was basic statistics, we built our foundation of statistics. There were 3 sections in it, and if you recall, in the first section, which was about fundamentals of statistics, we discussed about data, scales of measurement, population and sample, measures of central tendency, measures of position, measures of dispersion, and few other important concepts such as covariance, correlation, outliers, noise, and standard error. Then in the second section, we talked about probability and distributions. Now the topics are shown here. You can have a look at it. I'll not be going into the details of it. And then we also learned about different types of distributions and few other important concepts such as odds, log odds, confidence interval, population proportions, and central limit theorem. And then we moved to the next section where we discussed about the statistical hypothesis and its testing. We also talked about the concepts such as statistical significance, type 1 and type 2 errors, and then finally we discussed about the types of hypothesis testing. So that was all what we have covered in module 1. And now let's see what we have covered in module 2. So in module 2 we were introduced to R. So we learnt about R and the reasons for using it. Then we talked about the data structures and what are different types of data structures. Then in the next section we did some assignments in R. In total, we did 6 assignments in this section. So that is what we have covered in module 1 and module 2. Now let's take a look at the contents of module 3 that we are going to cover in the upcoming videos.
Okay, so let's start with the introduction of this module. Well guys, the next 2 modules are going to be long modules and their content covers almost 60% or more of the entire course. But this is the fun part because here you will get to know different algorithms, their theoretical concepts, and you will also implement them in R. Now as you can see, we have only one section in this module, that is modeling concepts. And it is divided into 7 different topics. We will start with a brief introduction to modeling. Then we will learn linear regression. After that we will learn logistic regression. These 2 algorithms are very commonly used. After that we have decision tree. Then we have naive Bayes algorithm. Then we have multinomial and ordinal log regression. And finally, we will cover resampling methods. So that is how this module will look like. We will first cover the theoretical concepts on each of these methods, and then we will do assignments in R to reinforce these learnings. Now starting with the introduction to modeling, we will be covering these 3 topics. First, we will learn about statistical learning. Then we will learn about the difference between regression and classification. And then we will learn how to assess the model accuracy. So without further ado, let's get started with our first topic now. So what is statistical learning? It refers to a vast set of tools for understanding the data. These tools can be broadly classified as supervised or unsupervised learning. In supervised learning, we have our training data on which we train our model. For example, we have a data that captures the properties of cherry, such as shape, color, etc. Now we will train our model on this data. Once our model is trained and fine-tuned, we will give it an input that has cherries and grapes. Now that our model is trained and know how a cherry looks like, it will be able to identify the fruit and will classify the new data as cherry or not a cherry. This is called supervised learning. Few examples are linear regression, logistic regression, neural networks, etc. We will learn all these algorithms in our course. Next, we have unsupervised learning. Here we do not have information available on training data with us. Learning takes place on the input data directly. It categorizes the data according to their similarities, patterns, differences, etc. Let's say we have our input data. We created our model and gave the input data to the model. Then it will give us the output by learning through our input data directly. So that is how unsupervised learning works. Few examples are cluster analysis, principal component analysis, etc. We will be learning these modules as well. They will come in our next module, that is advanced modeling. Okay, so the next question is, what is a model? A machine learning model is a mathematical representation of a real life process. And we use algorithms for building a model. And algorithms are a set of rules which is to be followed in calculations. So this was statistical learning in brief. Now the next question is, why do we need statistical learning? So basically there are two reasons. Either we are making predictions from our data or we are trying to draw inferences from it. Now let's say we have our input variables for selling a house. The input variables are location, price, expense on advertisement in different media, etc. Now based on this data, we may like to predict the sales. This is a problem of prediction. So here we can write a dependent variable y, that is sales. Now the dependent variable is also called as response variable. It is written as a function of x, that is predictor variables, which are location, price, etc. So y is written as y is equal to fx plus epsilon. Now what is epsilon? We'll just discuss in a while, but before that let's understand how we can estimate fx. Now we will not be able to know the exact function of x on which y is based, because we are not studying the whole population. So we can only approximate to the closest possible function, which will be an estimate of the actual function. Hence we will write y as a function of f dash x, indicating f dash x is an estimate. Now epsilon here is an error that is constituted of two components, reducible error and irreducible error. Reducible error is an error which arises due to the mismatch between the actual fx and our approximation of fx, that is f dash x. We can reduce this type of error by using better techniques or algorithms while building our model. So throughout our course, we will see how some techniques are better than others in terms of addressing this problem. But this is a twofold problem. We will learn more about it in a while when we'll see bias variance trade-off, which is another important topic. Anyways, the second type of error is irreducible error. This error is also called as measure of noise. This is an inherent error in the data. Like in our example, say we use 3 variables to make prediction. But in a real life scenario, there may be many more variables on which price of a house is dependent. But it is not possible for us to include all the variables for various reasons. So there will be some error due to such reasons. Hence those type of errors are called irreducible error, because they cannot be reduced by using some better techniques. So this was in brief what a prediction problem is. Now the second type of problem that we try to address by statistical learning is of inference. So sometimes you may not be interested in predicting the sales of a house. Rather you wish to know which of the variable has a greater influence on the sales. So you may like to know if your advertisement strategy is good enough or your prices are driving your sales, etc. So problem of these types are called inference problem, and we can use statistical learning to answer it. Now in our prediction problem, we said that we can express our dependent variable, that is sales, as a function of predictors, that is location, price, etc. We also said that we don't know the real relationship between y and x, but we will approximate it using estimate of fx. So the next question is, how do we do it? Well, there are two approaches for it, parametric approach and non-parametric approach. So in parametric approach, we choose a shape of the function. Say we choose a linear function as fx. So we can write fx is equal to beta naught, which is the intercept, plus beta 1 into x1 plus beta 2 into x2 and so on. Now once we find the coefficients, our model will be ready. We can substitute any value of x and can predict our sales. So here we assume that the relationship between y and x is linear, based on which we found out the coefficients, and then we can calculate the sales. Now the pros of this type of approach is that it is simple. You just have to find the coefficients and there you go, your model is ready. But at the same time there are certain drawbacks as well, such as the shape that we choose, like here we chose linear, may not match with the true shape. Maybe the true shape is not linear at all. In that case, our results will be unreliable. So in the second approach, that is non-parametric, what we do is, here we do not choose any shape. Rather, we attempt to find the estimated function that gets close to the data points as actual function. We will learn it later, but for now just understand that this is the main difference. Again, the good part of this type of approach is that it is more accurate, as it tries to mimic the actual shape instead of assuming anything. But the drawback is that we would need larger dataset and it is a complex approach. So this was a brief about the need of the statistical learning. Now let's move on to the next part. So there will be two types of problem that will come across: regression and classification. In regression, we have y, our dependent variable, which is quantitative, and we regress it onto our independent variable x. Let's say cost of production or sales, etc. While in classification, our dependent variable y is qualitative, and our aim is to classify this qualitative variable based on the independent variable x. So let's say we have colors, shape, size of cherry as our independent variables. So here we will try to classify a given fruit as cherry or not a cherry based on these independent variables. Now there are different algorithms that we will use to model these problems. However, there are methods that can be applied to both the problems. Also, all the methods that we will learn in our course can be applied irrespective of the type of the predictor. That means, irrespective whether the independent variable is qualitative or quantitative, all the methods that we are going to learn can be implemented. Now there is an important concept called bias-variance trade-off. First, let's understand what these two terms are. So first we will see what is bias. Bias is the error introduced by approximating a real-life problem using a simpler model. So as we saw earlier, we assumed a linear relationship and built our model, while in reality, the relationship may or may not be linear. So due to this assumption, there will be some error that will constitute to bias. Now let's say we build a model and it performed very well when we tested it based on our sample data. But then when we gave a new data, then the performance of the model dropped. This is called variance. Ideally, our model should be generic. Change in data should result in small variance. That is the whole point of modeling. We take past information and then predict the future. But if our model is not consistent, then the whole purpose is defeated. But the issue here is that we cannot reduce bias and variance together, because if we reduce one, the other will increase. That is why we will have to do bias-variance trade-off. So this is a complex and an important aspect of model building. So here in the below table, it shows what happens if we choose a simpler model such as linear model, which is easy to understand, explain and work, vis-a-vis if we choose a non-linear shape. Now this is a very important table, and I've compiled it such that it gives you a host of information in one place. So do keep it with you. You can refer to it in future as well. Now if you see the table, if we choose a non-linear model, which means our estimate fx resembles the actual fx, then flexibility of the model increases. The shape becomes more flexible. As a result, bias reduces, but variance increases. Hence, our prediction power becomes better because we have approximated our function to the actual function. However, our inference and interpretability of the results decreases because our model becomes more complex, and hence it can lead to overfitting. Now on the other hand, if we choose a linear model, which is a simpler model, then the flexibility decreases. As a result, bias increases, which means there will be more mismatch between our estimated function, that is f dash x, and the actual function, that is fx. Now the bias is increasing, hence variance will decrease. As a result, the prediction accuracy will also reduce, but it will increase the inference or interpretability of the results. Now this approach can lead to underfitting. So bias variance trade-off is basically finding the common grounds so that we neither underfit our model or overfit our model. Now it is easier said than done, but nothing to be afraid of. Just saying that it comes with a lot of experience and you will be doing it throughout your career. But I hope you have got a fairly good understanding of bias variance trade-off. Now moving to the next topic, which is model accuracy. So it is another important aspect of model building. So we will first see how we can test the model accuracy for regression, and then we'll see for classification. Now in regression setting, we see the average squared distance between the estimated value and the actual value. The smaller this value, the better our model will be. So MSE is given by the simple formula as shown here on the screen. Here we are differencing each predicted value from the actual training value and squaring it and then averaging it. MSE stands for mean squared error, and this is called as cost function in regression setting. We will use cost function everywhere in the modeling process. The purpose of cost function is to measure the performance of a machine learning model for a given data. So cost function quantifies the error between predicted values and the expected values and presents it in a form of a single real number so that it makes more sense to us and we can get a better idea of error. Now, depending upon the problem, we can either minimize the cost function or maximize it. The return value in case of minimization is called as cost, loss or error. And in case of maximization, the return value is called as reward. Our objective here is to select the model with minimum MSE. So obviously if the predicted response is close to actual response, then the MSE will be small. Now that we know that we have to minimize the cost function, the next question is how do we do it? So for this purpose, we use gradient descent algorithm. We will see this algorithm later on in advanced modeling, but just keep in mind that we use gradient descent algorithm to minimize the cost function. Now let's say these blocks are our data. So when we build our model, we split our data into two parts. So let's say we split it into 70-30 ratio, or it could be any other ratio. But let's assume we have split the data into 70-30 ratio. So one part of our data will be used to build the model, that will be called as training data. And rest of the data we will use to test our model. So this test data is a new data for a model. And if it can give good results, then it means our model is working fine. Now this graph shows the behavior of test and training MSE against the flexibility. So as flexibility increases, there is a continuous decrease in training MSE. But the test MSE follows a U-shape. You can see this in the graph. This is the fundamental property that holds true irrespective of the data or method that we use. Now don't ask why or try to go into the details. We just have to know this property and keep it at the back of your mind. Also, we are interested in test MSE and not training MSE because training data is used for building the model. So the performance of model will always be better on training data. So as a rule, training MSE will always be less than test MSE. However, if training MSE is very less than test MSE, then something is fishy and it means we are overfitting and hence we need to relook into our model. So this was the case of model accuracy in case of regression setting. Now let's have a look at the classification setting as well. So here we will be predicting a class of a response. So which class our response variable belongs to, like we did in our previous example of identifying a cherry or not a cherry. So here we will not use MSE. Rather, we must quantify the proportion of mistakes that we have made using the estimate function f dash or f hat. Simply put, it is the classification of observations to a wrong category or misclassification error rate. It is given by an indicator variable as shown here, which is denoted by I. This simply means it will be equal to 1 if the classification is wrong. That is, if yi value of an ith response variable is not equal to yi hat. And it will be 0 if it is correct. That means yi value is equal to yi hat. So yi hat is the predicted class level for the ith observation using our estimated function f dash. For example, when we tested our model using the test data, if the actual ith observation, which is yi, is cherry, but our model predicted yi hat as not a cherry, then it will be counted as one misclassification. And if our model predicts yi hat is equal to cherry, when the ith observation of the test data yi is actually cherry, then it will be counted as 0. So similarly, we will calculate for the entire test data and find misclassification rate, which is basically total number of wrong observations divided by total observations. Now here also we will use a cost function, and this cost function is called as cross entropy or log loss. The formula is shown here on the screen. Now as a general rule, whenever you see a complicated formula, just remember that you don't have to remember it. This will make life pretty easy. So just have a look at the formula. We will have software to calculate it, but you should know what is happening in the background. Now here also we will use gradient descent algorithm to minimize our cost function. So gradient descent algorithm is a generic algorithm. We can use it to minimize any cost function. So that was all about model accuracy in classification setting. So with this, we are through with the introduction to modeling. That was our first topic of this module. So what we have covered so far, we first saw what is statistical learning and why do we use statistical learning. Then we saw two different settings, which is regression setting and the classification setting. And then we saw how we can assess the model accuracy in both these settings, that is regression and classification. So we'll now be starting with our first technique, that is linear regression. So alright then, I'll see you in the next video. Until next time, see you.